Welcome to my Module 7 experiment for my Physics 1010 class. Today we will be calculating the speed of light using a microwave. Now before we explain the steps of this experiment, it's best to explain the underlying physics first. So the microwave is going to emit microwave radiation that's going from right to left. Once it reaches the left wall, it's going to reflect back and superpose on itself in such a way so that it becomes a stationary wave with nodes and antinodes. The nodes are the points along the wave where the amplitude of the wave is zero and it has no energy, whereas the antinodes are the points along the wave where the amplitude is at its maximum and so is its energy. So for this experiment, we're going to be using a microwave that will emit electromagnetic radiation at a frequency of 2450 megahertz, or 2.45 times 10 to the 9 hertz, as seen in the accompanying image. Now, I have one cheese slice, and we're going to put this cheese slice in the microwave at low power setting for 30 seconds so that it only heats it up at the particular spots. And we're going to, we put a ball at the bottom of the microwave upside down so that it doesn't rotate. Now, hopefully, the center of the melting points, or the center of where the cheese will melt, will correspond to the antinodes, specifically the antinodes in the downward direction, and the edges correspond to nodes of the stationary waves, as the wave isn't transmitting energy at those points and it's not melting the cheese. So we're going to be putting this cheese in now. Now that it's done cooking, it's time to take it out of the microwave. And yeah, we have two burn spots, one over here and one over here. They're also round, so we're going to be measuring the distance between the two burn spots real quick. Shortest distance as well. And we have, distance is about 6.6. Actually, hold on. Yeah, I would say 6.4 centimeters. So the distance from one node to another is 6.4 centimeters. Now that's going to be half the wavelength. So for us to find the actual wavelength of the microwave radiation, we need to multiply that by 2, which will give us 12.8 centimeters or 0.128 meters. Now, before we calculate the speed of light, we are going to look at the values for the frequency and wavelength of the microwave radiation and see if they fall within the expected range. The expected range for the frequency of the microwave radiation is from about 3.00 times 10 to the 8 hertz to about 3.00 times 10 to the 10 hertz, and our measured value of 2.45 times 10 to the 9 hertz falls within this range. Likewise, the expected range for the wavelength of microwave radiation is between 1 meter and 0.001 meters, and our measured value of 0.128 meters also falls within this range. Thus, both the measured values for the frequency and wavelength of the microwave radiation fall within the expected range. Now that we're done with that, we can go on with calculating the speed of light. The speed of light for any electromagnetic wave is equal to the product of the wavelength of that wave and its frequency. Thus, to calculate it, we simply multiply 0.128 meters with 2.45 times 10 to the 9 hertz to find that our calculated value for the speed of light is 3.14 times 10 to the 8 meters per second to 3 significant figures. A quick calculation for the percentage accuracy with the widely accepted value for the speed of light c, which is equal to 299,792,458 meters per second, we find that our value is only 4.61% away from the true value, and so we were fairly accurate with our measurements even with our very basic equipment and setup. Thank you for coming to my experiment, and I'll see you another time.